Hello, everyone. Welcome to another meeting of the seminar Symmetry in Newcastle. Today, we're going to be talking primarily about one-relator groups, so don't expect any more relations than just one. So the first speaker of the day is Charlotte Hoffmann from Austria, from Vienna. It's the Institute of Science and Technology, if I remember what those three letters mean.
Yeah, that's correct.
Okay, so Charlotte, the floor is yours.
Okay, thanks. And thanks for having me. So yeah, I want to talk to you about one-relator groups and in particular the hyperbolicity of one-relator groups. Right, and this talk I will present work I did with Christopher Cashen from the University of Vienna. And this is from a preprint that we uploaded just last year, so it's quite recent. And this is the main theorem that I've already stated there. So if we have a one-relator group and the imprimitivity rank of the relator is not equal to 2, and the length of the relator is smaller than, or it's 17, then the group is hyperbolic. Okay, and so this is just so that you know where we are headed. But yes, so I will start the talk with an introduction and some motivation, and I will start by defining hyperbolic groups, and so that we're all on the same page. And then in the second part, I will talk a little bit about the imprimitivity rank. And then in the third part, I will show you which methods we use to certify hyperbolicity of the groups. Okay, so let's start with the introduction. And so yes, we are interested in hyperbolic groups. And first, I want to give some motivation. So why are hyperbolic groups interesting? Well, this is because they have a lot of interesting properties. For example, you can solve problems that are in general undecidable. One example for this is the word problem. So given any word W, does this represent a trivial element in the group? So this is solvable in hyperbolic groups, for example. Also the conjugacy problem. So I give you two words and you tell me if one is conjugate of the other, or the isomorphism problem. Where I give you two group presentations and you tell me if that the groups that they define are isomorphic or not. Okay, and they have some more properties, but yeah, I hope this is enough to convince you that hyperbolic groups are actually interesting. And there are multiple ways to define hyperbolic groups. I will use the combinatorial definition in this talk. And so we have a group, and I have a finite set of generators, and I have a finite set of relators, like this. And I want the relators to be cyclically reduced. So this means I cannot have something like this here in my relator. And also the first element is not the inverse of the last element. And then I can define a Van Kampen diagram over this presentation. So this Van Kampen diagram is for some word in G that represents the trivial element. And then this is a finite, connected, oriented planar graph where all of the edges are labeled by generators. And then the boundary of the diagram is labeled by W. And we have that the boundary of all of the faces, they read some relator or the inverse of a relator. Okay, so the Kampen diagram looks something like this. I have some face here, which I don't know, if I read this in this direction, might read the first relator and then another face attached here. And I don't know if I read somewhere here, maybe this is the second relator, and so on. So can attach faces, and then so for our purposes, it's enough to say just that I can find some vertex, and if I start reading from this vertex along the boundary here, then this reads the word W. And the Van Kampen lemma says that for all words that are trivial in the group, there exists such a Van Kampen diagram, and this is a if and only if. So the word is trivial in the group if and only if there exists a Van Kampen diagram with boundary label W. Okay, so let's see an example. Take the group Z2, which has two generators and then the relator. And I take the word A squared, B squared, A to the minus 2, B to the minus 2. Now I want to construct a Van Kampen diagram for this. So I start with some face that has to be labeled by the relator. So I label it A, B, and then A to the minus 1. I denote by this arrow pointing in the other direction now, and then B to the minus 1. Okay, and then I can just attach the same faces like this. And now, if I start reading from here, I read A squared, B squared, A to the minus 2, and B to the minus 2. So this is W, and therefore we know that W is trivial in the group. Okay, another thing that I need is the notion of a reduced Van Kampen diagram. So I say that the Van Kampen diagram is reduced if we don't see something like this. We have here, which is labeled by some word A, and then two faces that are labeled by D, and also D in this direction. So here the boundary would read D times D to the minus 1. So this is something that we don't want in a reduced Van Kampen diagram. Okay, but this here is fine. So this is an example of a reduced Van Kampen diagram. And then for a word that is equal to 1 in G, I can define the area of the word. And this is now the minimal number of faces in a reduced Van Kampen diagram. With boundary label W. Okay, now I have everything I need to define a hyperbolic group. So we say that a finitely generated group G is hyperbolic if we can bound the area of every word linearly. So if there exists a constant C such that for all words are equal to 1 in G, we have that the area of W is less or equal C times the length of W. Okay, so the area is bounded above linearly in the length of the word. Okay, so let's see some examples. The first example are finite groups. Finite groups are hyperbolic. And why is that? Because for finite groups, you have a presentation like this, where the generators are just all of the group elements, and then the relators are all of my multiplication rules. So they look something like this: gi times uj is equal to gz, and so on. Okay, so, and then if I have some word that is trivial in the group, then I either have that the length is already 3, but then w is just some relator. And so I have that the area of w is 1. Or if the length is larger than 3, then I can just, I write the word like this here, for example, and I just take the multiplication rule for the first 2 elements, and then I get some shorter element, and then I repeat until I arrive at a word of length 3. And this is, and this process is the same as saying we have some relator here, like this, and then the Kampen diagram looks something like this. And if I cut off this face here, then the length of the boundary gets shorter. And so I have that the area of W is bounded above by the length of W. Okay, another example are finitely generated free groups. But you see the only word that is equal to 1 in G is of course only 1, and the area of 1 is 0. So that this is another example. Okay, and we will see more examples later in the talk. But first, let's see some non-examples. Okay, so one group that is not hyperbolic we have already seen. This is Z2. And this is because the area of a to the n, b to the n, a to the minus, and b to the minus n is n squared. So it cannot be bounded above linearly. We saw this, so here in our example, we have the exponent 2, and the area of the word is 4, because this I have 4 faces here. And yeah, you can show that it's true for all n, and so this group is not hyperbolic. More generally, you can say that all Baumslag-Solitar groups are not hyperbolic. That are groups that look like this. I have A, B, and then B, A to the m. B is equal to A to the n for some m, n in Z. So Z2 is an example of a Baumslag-Solitar group, and you can actually show that none of those groups are hyperbolic. And even more, you can say that any group that contains a Baumslag-Solitar group as a subgroup can never be hyperbolic. So no hyperbolic group can contain a Baumslag-Solitar group as a subgroup. Okay, so, but what about other non-examples? So as you see, all of the non-examples I've shown you so far are just some groups that contain Baumslag-Solitar subgroup. And then the question is, are there more? And this is actually a very important question that has been open for quite some time. So this is also the first question on Westlina's list, which is a collection of open question geometric group theory. And this asks, so if G is of type F and has no Baumslag-Solitar subgroup, is it then always hyperbolic? Okay, and I should say this type F here. This means that there exists some finite space X such that our group is the fundamental group of this space, and the higher homotopy groups are trivial. Okay, because it turned out that you need something like this, otherwise you can't find counterexample. tests for the questions, for the question. But yeah, so the question, like it's stated here, is still open. And now in our paper, we considered one-relator groups. And why are they interesting to us? So the first thing is that one-relator groups are always of type F. Okay, so now we only need to take care of the Baumslag-Solitar subgroups. And then there is a recent result by Lauder and Wilton. This is from 2018. And this says the following. So if I consider a one-relator group like this, and then they consider the imprimitivity rank of the word W, that I will define later on, just a bit. Yeah, I will abbreviate it I rank of W. And then the result says that any subgroup that is generated by fewer than I rank elements is free. Is free. Okay, so but what does this mean for Baumslag-Solitar subgroups? If we go back to the definition, we see that they are always generated by two elements. Okay, so if the imprimitivity rank of the word is larger than 2, then it cannot contain any Baumslag-Solitar subgroups. And therefore they conjecture. So this is the conjecture of Lauder and Wilton. They say if we have a one-relator group and the I rank is larger than 2, then the group is hyperbolic. So our one-relator group. Okay, and so now back to our theorem. So this theorem supports the conjecture because, yeah, we show that there are no small counterexamples to the conjecture. So if we have a one-relator group and the imprimitivity rank is not equal to 2, and the length of the word is less or equal to 17, then G is hyperbolic. Okay, and then so you might ask yourself, why this 17? Where does this number come from? Well, this is because we proved this by computer computation. And so 17 was our limit, but yeah, so we were trying to show that there are no small counterexamples to the conjecture to maybe yeah, to strengthen it. Okay, and so this was the introduction, and now we come to the second part, where I will finally tell you what this imprimitivity rank is about. Okay, so if I consider some word in a free group of rank n, then I say that this word is primitive if it belongs to some free generating set of Fn. Okay, and it has been shown that a primitive element is primitive in every subgroup. Okay, but what about imprimitive elements? for those, we don't have a result like this. So if the word W is not primitive in Fn, then it could be either primitive or not primitive in a subgroup. And so in this case, Puder defined the imprimitivity rank in 2014. So I take a word in a free group, and then the imprimitivity rank, or the I rank that we're now rated, is the smallest rank that a subgroup can have that contains the word W as an imprimitive element. So minimal rank of each n in W as an imprimitive. Or if no such H exists, then we say the rank is infinity. Okay, so let's consider the values for the imprimitivity rank, where we already can say something about hyperbolicity. So first, if the I rank is equal to 1, and then this means that the word is a proper power. So this means W is a proper power. But in this case, B.B. Newman has shown that the group is hyperbolic. So I can write the one-relator group like this. And yeah, so this here we already know that the one-relator group that has the generator W is hyperbolic. Okay, what about the case where the I rank is infinity, where this means that W is a primitive word of Fn. So primitive in Fn, but then you can show that the one-relator group with relator W is isomorphic to the free group of rank n-1, and we already know that free groups are hyperbolic. Okay, then in the case where the I rank is equal to 2, there basically anything can happen. So we have there are examples where the group is hyperbolic, and there are examples where it's not hyperbolic. So according to the conjecture, this is basically the case where it's still mysterious. And then what we considered is a finite rank that is larger than 2. Okay. And now I will shortly say a few words about how you can compute this imprimitivity rank. And for this, we first need to enumerate the subgroups that contain W. This you can do with Starling's graphs. And then in the next step, you have to check primitivity in all of those groups. And for this, you can use a result by Whitehead that says that the word is primitive if and only if there exists some automorphism. So F is now just any free group, such that if you apply the automorphism to W, then this is length 1. And then whitehead also gives you exactly how those automorphisms can look like. And so you can check if you can reduce the length of the word. And if you can't reduce it anymore, then it's not primitive. But if you arrive at length 1, then it is primitive. Okay. But I think I leave it at that and then get to the third part, which is about certifying hyperbolicity. Okay. And for this, we used different checks. The first thing we did, which is quite easy to check, those are small cancellation conditions. And if they didn't work out, the second thing that we used is some relatively new procedure, which is some curvature redistribution. And this was presented by Hold others in 2019, I think. And they also implemented the procedure in GAP. The package is called Walrus. Okay, so this was the second thing we used. And then there were still some groups left that those two checks didn't catch. And in this case, we used the KB-MEG package of GAP. And so this is a procedure that is guaranteed to hold at some point if the group is hyperbolic. So it will tell you that a group is hyperbolic at some point, but for our purposes, this was a little bit too slow to just try out all the groups with this, because for our groups it took around 2 minutes for one group, and so therefore we did the other checks first. Okay. So I think I would quickly say something about the small cancellation conditions. I guess many of you already know them. So yes, so just let me tell you some. I will just show you one example of a small cancellation condition. So again, we're looking at some group, finitely generated, and then I have now the set curly R here, a set of relators, and I want this to be closed under inversion and cyclic permutation. And then I define a piece. So this is if I take two elements from the set curly R, such that they both start with the same subword B, then this subword B is called a piece. So a piece is just a subword that occurs in multiple elements of this curly R. And then we say that the group G set lambda if for all of the elements in here that looks something like this, where B is now a piece, we want that the length of the piece is less than lambda times the length of the relator. Okay, so basically this says that the pieces are small enough, and then there's a classical result by Greenlinger that says if the group satisfies C prime 1/6, then it's hyperbolic. Okay, so this is just one example of a small cancellation condition. And with this, I can give you an example of another hyperbolic group, namely the fundamental group of a closed orientable surface of genus 2. So for this, we have this presentation, and I think I will write out the relator. So 2-1, A2, B2. Okay, because then this way we can see that the only pieces are single letters. And why is this? Okay, so the single letters are pieces, because if I see this letter A1 here, this occurs another time in the relator. And yeah, remember, so R is now closed under inversion and cyclic permutation. So the single letters are all pieces, but there are no pieces of length 2. So if I take, I don't know, this separate here, A2, B2, then this does not come up again in the relator, and also the inverse B2 to the -1, A2 to the -1 does not come up again. And so this is not a piece. Okay, but then we know, okay, the length of the pieces are just 1, the relator is of length 8, and so I have C prime 1 over 7, and then in particular I have C prime 1 over 6, and so the group is hyperbolic. Okay, and there are some some more small cancellation conditions that we checked first, because they are quite easy to compute. You just need to find the length of the pieces. And if this didn't work out, we use this curvature redistribution.
Could I ask a stupid question? How often does this work out? I mean, how many words are we talking about, and how often does each check? Yeah, I'm sorry, does that make sense?
Yeah, sure.
Social amateur, just asking a silly question. My apologies.
No, that's great. So there's a result that says that almost all groups are C prime 1 over 6. So if you generate a random group, it will most likely be C prime 1 over 6. I don't have the exact numbers in our case, in how many cases this worked, but I will tell you some more about the numbers later. So how many groups we checked and everything. I have prepared some tables later.
Thank you very much.
Okay, welcome.
To partially answer Saul's question and to advertise my own stuff, we recently had a paper with Alex Bishop where he actually worked out exactly what these densities are for small cancellation groups, or got a tight estimate. So you could look that one up as well. We have measurements and all that. Okay, enough of my advertisements.
I guess the question is, does the computational results seem to verify the density work? But that's not really, that's a question for the end, so I apologize. Thank you very much.
Okay. Okay, good. So let's head to the second part. So this curvature distribution. Okay, so for this, I'll have this theorem that if you have a finite presentation, and then now I will assume that all relators are of length larger than 3. So in the original theorem, they don't assume this, and this is actually one of the strengths of their procedure, that you can have very small relators and still prove hyperbolicity. But for our cases, yeah, so then the theorem will look a little bit more complicated, and I only need the cases where they are larger than 3, so I will include this here. And then if there exists some epsilon such that for every one Kampen diagram, over P, so there we do the following. First, we assign curvature +1 to faces and vertices. And then -1 to edges. And then in the next step, every edge gives half of its curvature to an end vertex. So to both of the end vertices. vertices. And then in the last step, now every vertex divides the curvature equally amongst all of the incident faces. Interior faces. Yeah. Okay, so we do this procedure, and then if afterwards we can bound the negative curvature by all of the non-boundary faces by some negative number, then the group is hyperbolic. So then P defines a hyperbolic group. Okay. So this description is maybe a little bit abstract, so I will show you a concrete example how this proceeds. So let's take this group here on the generators ABC, and then I have this relator. Okay, so first of all, this small cancellation condition I showed you earlier, C prime 1/6 is not satisfied because here A2 is a piece, and this is of length 2, and the length of the relator is 8. Okay, so this does not work out, but with this new theorem, we can show that it's hyperbolic. And how do we do this? Okay, so again, look at a Van Kampen diagram, and we'll now look at a non-boundary face. So the face is labeled by the relator, like this. And now non-boundary means that the diagram, I don't know, goes on like this, and there's no edge incident with the outer face. Okay, but this also means that the vertices all have degree at least 3, because there are some other faces adjacent, and all of the faces are labeled by some cyclic permutation of this relator, because we only have one relator. Okay, and now what does the procedure do? First, we assign +1 to faces and vertices. So the faces curvature +1, and then yes, for example, this vertex has curvature +1, and now the edges have curvature -1 and give half of it to the vertices. So if this vertex has degree 3, then it will get -1/2 from this edge, -1/2 from this edge, and then -1/2 from this edge. And so it ends up with curvature -1/2. And then in the next step, it divides the curvature equally between the incident interior faces. And so it has curvature 1/2, and let's say it's incident to 3 faces, then it gives -1/6 to every face. And also to this one here, -1/6. Okay, good. Now the face has 6 vertices, and the degree is at least 3, and so it gets curvature -1/6, at least curvature -1/6 from each vertex. But then we would have the total curvature of 0, which is not enough, because remember that we need to show that we can bound the curvature above by some negative epsilon. And therefore, the only thing we need to do to show that the group is hyperbolic is just show that some vertex has degree larger than 3. Okay, I will show that this vertex is a vertex of degree larger than 3. And why is this? So look at the face that's on the other side of my edge B. So this face here. So this face is also labeled by the same relator, but now this B, so the label of this edge, which corresponds in this face to this B here. In the other face, this has to correspond to the other B, otherwise it would not be reduced, and we would just have, yes, here D times D to the -1, as we've seen before. And so therefore, in this phase, the next edge would be labeled by this element here, C to the -1, C to the -1. And then I can look at this phase here on the other side of the edge labeled by C, and see that this cannot be an edge of this phase, because otherwise I would read the subword, if I read along here, I would have the subword C squared, but this is not a subword of our relator. And so therefore, I know that here has to be at least one more edge here. And so this is it, this concludes the proof. Therefore, then this vertex gives curvature -1/4 to the face, and we're good. And so therefore, we know that G is hyperbolic. Okay, so so this was the other check we did, and then yes, we saw that if the length of the relator was length, so let's write it like this. W was less or equal to 4 times n, where n is the rank, then this was always enough, so we didn't have to use KBMac in those cases. And then if it was larger, then it was more complicated, and sometimes we used the KBMac procedure. But it was yeah, it wasn't too many groups, and so we were able to do this. And then also one thing I should note is that we computed this up to rank 4. So groups of rank 4. But then if the rank is larger or equal to 5, and remember that our words were larger or equal to 17, then we know that there exists some generator such that this number here is less than 4. And so this denotes the number of times this generator A or the inverse comes up in the word. And so in this case, yeah, there exists just one, there exists one where it's less than 4. And then there are some roots by Ivanov and Schub. And they tell us exactly, if we have something like this, they can tell us exactly when the group is hyperbolic and when it's not hyperbolic. And it turns out that all of the cases where it's not hyperbolic, the imprimitivity rank is equal to 2. So they give cases where, okay, let's write it like this. Not hyperbolic, and it turns out this implies imprimitivity rank 2. And therefore our theorem follows. And then, okay, let's see some numbers. I think I have them here. Yes, okay. So, okay, so here's a table of how many groups we have checked. Up to length 16, right? Because for length 17, we first did the checks and then afterwards enumerated the groups and computed the imprimitivity rank, because this was just faster this way. But yeah, so those are the groups, and then here just some numbers on the imprimitivity rank. So you see that in most cases the imprimitivity rank equals the rank of the group, and yeah. So that's all that I wanted to say, but I'm happy to take questions.
Okay. Thank you, Charlotte. Do we have any questions?
I'll try and re-ask my question, but maybe my question doesn't quite make sense. Saul Schleimer here. So you said you had 3 tests for verifying hyperbolicity. So I guess what percentage of the time, like when L is as large as it gets, what percentage of the time does each test need to be used? I guess since you did them in that order, the first one is the most effective, and so on.
Yeah, no, I understand your question, but I don't have the numbers. I don't know.
Oh,
I think I
I'm sorry.
can't give you an answer. Yeah, it just.
Well, like just your impressions, was KB-mag used like a single digit number of times, or was it actually like when actually got to that, to KB-mag a significant number of times?
I think no. So no, all I can tell you is that it was not so often such that the experiments could be completed. But no, I think I had to check. I have to check again how many times we had to use this.
Well, thank you very much, and thank you for the talk.
Okay, thanks.
Any other questions for Charlotte? Well,
I'm interested in the cases where you couldn't prove hyperbolicity using your walrus package, but you could prove it using KB-mag. Can you say something about that? I mean, I thought walrus was meant to be better than KB-mag in every conceivable way, but it's not.
No, so I mean, this procedure, here that I showed you, and the way that it's implemented, this is actually not at the full strength. So you can extend the algorithm and say that some neighboring faces that have a lot of negative curvature, say this one here has, I don't know, -304 curvature, then those can also give some negative curvature to their neighboring faces. And with this, you would catch more groups, but this is not implemented in walrus yet. And so, yeah, so there were some groups that this walrus didn't catch.
Sure. Okay. Thanks.
all right. Any further questions for Charlotte? Well, it seems that we do not have any further questions, so let's thank Charlotte for the talk one more time. Charlotte.
Thanks.
And now it's we have a break for coffee and tea, or if you're in a different time zone, beer. We're not going to judge, and we can meet for the next talk in about 30 minutes, well, 40, something between that.